Hello everyone. Today we'll discuss on the some other topic after on the panel meters and the frequency measurements. Okay. Here there are three different types of meters. There's digital panometer, bench type meters, and the system type. First one, the digital panometers. Digital panometers are usually made available in the very wide range of special purpose function. They usually read out three basic digits to high precision of 4 3 by 4 digit. The usually units what are available here, they accept the inputs such as DC voltage, AC voltage, line voltage, strain gauge, bridges, RTDs, thermocouples of many types, and frequency inputs such as pulse tachometer. So these are the various applications where we will be using the digital parameters. Not everywhere which you can benefit the digital parameters. So this week usually we are, as I said, it's very available everywhere. Usually this has three state binary coded decimal output. This is the tri-states you might have done: high, low, and a high impedance state. Okay, you might be knowing in the digital logic that high on, low off. This lies in between the different range. That's we call it as a high impedance. Okay, so you might have doubt here. What is that for 3 by 4 digit? For 3 by 4 digit. So four digits will be there, and some points, everything will be the digitals will be escaping. So that we usually call it as a 4354 digits. Next one is the bench type meters. These bench type meters are usually inexpensive and usually held units up to 3.5 digital units, readouts. And usually we have a zero point 0.5 accuracy to 5.5 digital devices with 1 microvolt resolution. What is that 1 microvolt? It's a very small responses which can be captured. That's a small change, slight change also you can be captured. There are again some three categories. So depending on their application, digital nanovoltmeters. Usually they are designed to measure extremely low voltages with a resolution down to about 10 nanovolts. Very rare, usually the voltages will be very high, but these are the special devices designed for only about about 10 nanovolts. Next one is the digital picometers. They are usually measure very small currents and can resolve up to 1 picoamperes. You know what I mean 1 pico. You're very familiar with it. Next one is the digital electrometers. Usually are used to very high impedance is needed for the current. Okay, and voltage, resistance, and all. To not to have any fluctuation, you have to stabilize that. And sometimes for the to control the process, usually we use this one. It can resolve up to 10 raised to minus 17 amps, 10 microvolts, and 1 femto charge. Femto stands for 10 raised to minus 15. You are very not familiar very. And you can measure up to resistance as high as 20 theta ohms, or we say it a tera ohms. Okay, not theta, tera. So the input impedance can be as high as 10,000 tera ohms. Okay, so now we discuss about the system type meters. System type DVM or DMM multimeters, okay, digital multimeter, are designed to provide the basic analog to digital conversion function in a data system assembled by interfacing various peripheral devices with DVM capacity, and their cost vary widely. This might be a concept where we'll be using some of the, like when you're interfacing to the microprocessor, recording some analog to digital functions there. We are capturing the voice and we are trying to convert it to digital, the songs, the movies, everything. So they are specifically designed, and similarly, sometimes we capture the voltages also for that. Usually, we provide the microprocessor, usually uses the mathematic function for addition to managing their meter operation. A modified dual slope 8 analog to digital converter. I think you might be familiar with the dual scope analog to digital converter. For this selectable integration of time. So why this? So we can have only the time there, peak times and raise down time, which is ranging from 0.01 to 100 power line cycles. At maximum speed, that is 330 readings per second. At maximum speed, 330 readings per second, the accuracy is plus or minus 0.1 second percentage, while 0.57 readings per second gives a 6.6 and a half digital resolution and a 0.001 percentage of accuracy for the 0.6 and a half digit resolution. For AC DC volt and resistance modes are available. As I said, these are the usually used for the system for the with the help of a microprocessor. They usually provide this thing. So we need to consider some of the factors in this one. Okay. Next, the digital frequency meter. The digital frequency meter, how it will be converting. Or here, the basic is the signal waveform has been given and converted to the trigger pulses by applying continuously to an AND gate. You can see the below figure on the left side. What we are doing, a pulse of 1 is applied to the other terminal and a number of pulses counted during this period indicated the frequency. So what we are doing here, a frequency has to be captured for a continuous for 1 second, for example. We give a certain number of pulses there for that to make it working. After that, we make it okay. We don't provide pulse. So amount of pulses provided during that one cycle. For example, here I am taking it as a 1 second. So that much time that pulses will be recorded at the output. So it will be like converted into a train of pulses. Yes, you can see it over there. And one cycle will have n number of pulses. In the case figure, you can see around 6 to 7 pulses there. So these pulses which are occurred is usually of a definite interval of time, and these are counted by the counters. Usually some are given to the, as I said, to the microprocessor or anything, depending on your application, dependent. So what is done? Unknown signal can be given, a number of counts of a this pulses can be captured, and that gives determine of the frequency of the signal. And the counters usually they have high speed of operation and high frequency signal can be measured. A very good example is like when you go to a parking lot. What we do when a car is passed through it, an interface or a interrupt will be occurring. So that interrupt is given as a one count. Till that the continuous the pulses will be going. Sometimes it might be vice versa depending on how the mechanisms have been designed. So whenever a car passes to that ray of signal, automatically its interrupt will occur. That is, the ray of signal is not passed through the one end to the other end. So that time it is counted as one. Similarly, how many cars are when sent in and how many cars are sent out? If the mall or the security people cannot record all these things, then it will be within the checking part. So what will happen? So this very fast will be required. So below there's one block diagram where we'll give an unknown frequency that which is little multiplied. Or we say the amplification is in general we say as multiplied. We usually say amplification. And what is that amplification? If a signal is given and we are just multiplying the things. Sometimes amplifier will be having inbuilt attenuator to remove all the unwanted signals. So that signal will be there that will be multiplied into 1 or 2 or 3 or something amplified and we are giving to it to this discriminate trigger. What is skim trigger is doing? It converts that input signal, whatever the sine wave anything, into a square wave. The raise time and the fall time. So these are differentiated and clipped. As a result, the output of this schematic trigger is a train of pulses. So what is that? Start, stop, the pulses will be given. So that count will be counted by the counter cell. So when the gate is disabled, the counter stops incoming counting the incoming pulses. When this is given to the gate, when it's enabled, start counting the pulses. Okay, so you see the time interval between start and stop is taken as a one interval. So as we know, f is equals to 1 by t. So that logic again we are using it here. The next one is the basic frequency measurement. So here, first the output of the unknown frequency is applied to the schematic trigger, and the square pulses have been provided to the main gate A. And at the another end, the reference is what we need to be used there. The pulses from the time-based selector will be given. Okay, that input will be provided to the both the B input or the start and the stop gates. Initially, we need to reset flip-flop -1. So that has been given, the pulse has been given to the R of F, flip-flop -1. Then, so that time, Y will be 0, Y -1 will be 1. Y will be 0 and Y minus is, so that time what will happen, Y is 1 and that is given as an input to the A to the stop gate. So that time 1 and 1 of B, 1 A is equals to 1 and B is equals to 1 in the stop gate. So that is given to the bit as 1 to the flip-flop -2 gate flip-flop. Okay, then we'll come back to later there. Another at the output of Y bar. So what is happening? It is giving it as 0. It is giving it as a 0. So that is given to the a 0. So here in the start gate, A is equals to 0, B is equals to 1. So output is nothing but 0. So start gate is disabled and here stop gate is enabled. So what is happened? Stop gate is enabled means it is the setting S is equal to 1. So flip-flop -2 is what is happening. Y is equals to 0, Y is equals to 1, but Y bar is equals to 0. So that is supplied to the B and at the main gate, and that is given to the counter. So it is what it is giving, Y bar is equals to 0 and A is having, so it is making it reset and start the counting. So similarly, again the next one is given back f minus flip-flop -1 from the start gate as the output is 0, that is again fed back as to set. So that time it is given as y is equals to 0. So y is equals to 0 in the stop gate, a is equals to 0 and b is equals to 1. So that time it is disabled and y bar is 1. So it is given to the b is equals to 1 and a is equals to 1. So start gate is enabled now. So that is given as the R. So that time the y is 0 but y bar is 1 and that is given as the input to the main gate. So what is here? It starts giving the pulses and starts counting. Similarly, and that start gate again is taken back and it is stopped. So the start gate, the output is 1, so it is given back here again y stop. Similarly, this passion will be going on with respect to the bit given there. Okay, so what is happening between the start and the stop? What is the time interval? That is, the counter is counting that, and that is measured, and that is given back to the interval, that is t, and f is equals to 1 by t. Usually, this y bar is called it as a gating signal. That is, it is input given to the what it is. Because of that gate will be enabling the main gate. So whatever the count, start or end, everything is done because of the gating signal itself. So what we are doing, we have here mainly this process. Unknown signal is passed, comparing, and we're trying to see the start and the stop work and counting the time interval for which time interval the pulses have been captured. So logic behind is what? We need to know the proper start and the stop bit. That interval has been got and that has been calculated. And that is visually done by the counter. So what is the counter curves? The pulses occurring between the two successive pulses and from the time-based selector. So whatever this is there is counted at the counter. Okay. So this is what the basic frequency measurement circuit. Next one, the basic circuit for frequency. So another form. So what is the advanced one? I'll be explaining. Here you can see a circuit. The time interval between the two successive pulses can be captured from the time-based selector. If it's one, if you consider a case, the number of pulses counted within this interval. If you set a time for 1 second or 10 second or 20 second, we need to set a range and we have to count the pulses counted during this interval of an unknown frequency source in hertz. Okay, this consisting of an assembly consisting of a two flip-flops and two gates is called a gate controlled flip-flop, as we observed in the previous. That's it. Now, this block diagram shown here, the frequency, how it operates. That's the thing. Input signal is amplified, converted to square wave by a schematic trigger, differentiated and clipped into person train of pulses. Usually, they're separated by a period of input signal. So here the time-based selected output which are generated. So here we have an option. You might have seen the frequency with the different ranges, one to some range, the 1 kilohertz, 2 kilohertz, 3, 10, 20, 1 kilo, 1 mega, so like that, etc., etc. So this is how the operation works there. So ranges we are need to select. So what you are doing, so 1 megahertz crystal oscillator has been given. The signal is creating that signal what we got is by oscillating the crystal oscillator. That will be working in your lab there, oscillating of it. Here we oscillated like a thing. We're not giving a supply. We are giving just energy to it. It's act as an active source. The signal what is generated is given to the schematic. We are not telling the 1 megahertz to give a continuously this one. It's setting 1 megahertz is it can vary from 0 to 1 megahertz the oscillator, which is designed in such a way. So provided to the schematic trigger, the square wave is generated. And then it is divided by 10. First is whatever the signal is divided by 10 is 1 mega microsecond. Next 10, 100, 1 milli, 10 milli, 100 milli, 1 second. So these are the different ranges which has to be selected by the time-based selector mode, and that again is provided to the schematic trigger, and which is given to the gate flip-flop which is trying to enable or disable. So we have to set the period of duration of which the pulses has to be captured. So from the unknown frequency source, regularly the data will be coming to which one? Data will be coming to the amplifier, schematic trigger, everything, and it's provided to the gate by a triggered pulses. But we need to enable that main gate by using this time-based selector of a generated by 1 megahertz crystal oscillator for a duration of time, or by a recording which is required for selecting any of the different. Understood this topic? This is like we need to not worry about too much of that concept. Just look at the what is the principle of operation, what it is doing. You need to write that. Okay, look for that concept here. And basically, what we are looking here is for two frequency. Remember one thing: the basic principle f is equals to 1 by t. So if we capture time, we can capture frequency. So this is one direct method, not a direct actually. You can say it as f is equals to 1 by t. So we need to capturing of t, then we need to count the pulses string, then we give it the time interval. That okay. But I think it's one of the very good technique. Okay. So these are my references: HSLC, electronic instrumentation. So other two are the extra reference books. Thank you.